So again, if you don't have a calculator, you're going to want to grab one because we're going to have to do some calculating like we did yesterday. So we're going to continue the Riemann sums. We started with left hand yesterday, then we went to right hand. Again, having that vertex touching the curve on the left side or the right side. On the next two approximations, we are going to do a midpoint sum. That is, draw your rectangle so that the upper right-hand vertex of the rectangle... Okay, yeah, so that is the one, Daniel, you mentioned yesterday, right?
Yes.
I think the directions in this one are actually wrong. You should draw the rectangle so that the midpoint is on the curve, so it's not the right-hand vertex on the curve. So if you want to cross that out, the right-hand vertex should not be on the curve. The midpoint is going to be on the curve. So again, we're dealing with the same function as yesterday, dealing with the same interval. Again, we're just approximating it in a different way. So on the interval from 1 to 7, subdivide the area bounded by the graph and the function and the x-axis into rectangles. Again, this one is length 2. So again, we're starting at 1 and going to 3, so the midpoint has to be at 2. So at 2, and 1 unit to the left, 1 unit to the right. That's your first rectangle. So at x equals 2 is where it should be touching the curve. Then your next one, the midpoint's going to be at 4. And then your last one, midpoint will be at 6. All right. So now again, we're approximating the same thing as yesterday, integral from 1 to 7, f of x dx. Approximating. What is in common with these rectangles? They're all the same length of what? 2. Remember, we're trying to find the area of each one. Length times width. Well, they all have a length of 2, so the 2 can be pulled out in front. Now we just have to find the width of all of them. So again, everywhere your point is on the curve, that's the value that you're calculating. So what's the first value of f that I'm calculating? F of what? Yes, f of 2 plus f of 4 plus f of 6. Go ahead and calculate that one. F of 2 plus f of 4 plus f of 6 multiplied by 2. Again, you may have to look back for that function. Again, since we're approximating the same function as yesterday, your value should be relatively close to the last two examples we've done yesterday. So once you calculate your value, look back, see if you got something relatively similar. If it's way different, then you did something wrong. It should be similar because we're estimating the same curve. All right, I still see people punching into their calculators, but did anybody find a value? Anybody get an approximation out there? Go ahead.
40.667.
40.667. Now again, if we look at it, this one looks like a little closer approximation because of the midpoint. There's less overhangs and underedges. But do we think it's probably a little bit of an overestimate or a little bit of an underestimate? Yeah, I think it's probably a little bit of an overestimate. All right. Any questions on the first one? All right, go ahead and start on the next one. Again, midpoint, but this time they are 1 unit. 1 unit. So at 1.5 is where your first one would be on the curve. Then 2.5. 3.5. Again, estimating from 1 to 7, f of x dx. The width this time is 1, so that's your coefficient out in front. Again, calculate everywhere you have a point. Is there anybody that's having trouble figuring out the answer or not getting the same answer we got for any of the previous examples? Because as we go on, that way to speed up the example some, if you're okay with how to calculate, I'm going to give you some answers for this. So is there anybody that's still having trouble calculating the answer? Or if given the right amount of time, are you okay with calculating it? Anybody need a refresher on that? We're okay with that? All right, so again, I didn't write down all the values here, but we're going to have f of 1.5, f of 2.5, 3.5, 4.5, 5.5, all the way to 6.5. So I put ... in the middle. And again, after calculating this approximation, we would get 40.167. And again, do you think that's a little bit of an over or underestimate? Over. A little bit of an overestimate. Any questions on either of these two? All right, if there's no questions, we'll go ahead to the next page. So we're going to look at the next type. So we've done left hand, right hand, and midpoint. The last one we're going to do here is the trapezoidal. So on the next two approximations, we're going to draw trapezoids between the curve and the x-axis to approximate the area. Remember that the area of a trapezoid is found using the formula. So this is the formula we're going to have to use this time for finding area. It's not just length times width anymore, like a rectangle. This is the new formula for area, where B1 and B2 are the parallel sides, and h is the distance between those parallel sides. Again, same curve, same interval. We're starting with units of 2 again, but we're changing the shape and how we calculate it. So we're drawing a trapezoid. So from 1 to 3, because we're going 2 wide, we're going to have a point here and a point here, and we're drawing that trapezoid. Okay. So again, we're going to have an endpoint at each side. Then we go 2 more. Well, from here to here is 2 more, so we're drawing the next one. Then from here to here. Before we do any calculating, visually looking at it, do you see how it's going to represent a closer example of what the true estimate would be? All right, so ultimately we are doing the same thing. Integral from 1 to 7, f of x dx. We're trying to find the area under the curve. But this time, remember, the formula is going to be a little different because we're dealing with a trapezoid, not a rectangle. So this is going to differ some. Finding the area, we know we have 1/2 times the height. What is going to be considered the height of each of these? 2. They're considering the height. I know it kind of seems like a width or something like that, but the height they're considering as a 2 because they defined h as the distance between the parallel sides. So the distance is going to be 2, or the height. So 1/2 times 2, again we're referring to this formula from up above. Now we have B1 plus B2. Well, what is B1 and B2? What do those represent? What do B1 and B2 represent? The length of the parallel side. Well, how do you find the length of the parallel side? Or just one of them, for example. Yep. So we are going to have f of 1 plus f of 3. So again, this is just calculating the area of one trapezoid. 1/2 times 2 times the quantity, f of 1, that's this value here, and f of 3, this value here. Did I lose anybody? All right, again, this is only for the first one. Now we got to do the second one. Plus 1/2 times 2 times, well, this time it's f of 3 and f of 5. Okay, so that's for the second trapezoid. And then we have one more left. Again, 1/2 times 2 times f of 5, f of 7. So before you go and calculate that, let's write a simplified form to maybe make that a little bit easier. So again, this is individually the area of each one. So a simplified form, well, each of them have a 1/2 and each of them have a 2. So 1/2 and 2 out front. Again, ultimately, those will cancel, 1/2 and 2, but I'm just writing this form so we can visualize where everything's going. So 1/2 and 2. And since we pulled those all out in front, we can add everything else together. Well, we have an f of 1. So f of 1 plus, I actually have two f of 3s. F of 3 plus f of 3. So 2f of 3. Then I have f of 5 and f of 5. I actually have two of them. So 2f of 5. And lastly, f of 7. So this is what you're calculating for the estimate on this one. 1/2 times 2 times f of 1 plus 2f of 3 plus 2f of 5 plus f of 7. I am going to let you guys do this one since this is the first trapezoidal one we've done. Again, we're approximating that same function from the beginning, so you're using the same function, but this is how we're going to have to calculate the area on the new one. Again, since we're approximating the same curve, you should get a value that's relatively close to the values we have gotten with every other example so far from yesterday and today. Yeah, it's the same equation from yesterday. We're doing the same approximations as yesterday, we're just using different methods each time. So if you notice on the graph, we're approximating the same curve as yesterday. Same interval, same curve, same functions. We're just using a different method each time. Ultimately, we're going to see what provides the best estimation of all the methods. Anybody find the value out there? Go ahead, Steve.
38.68.
Yep. I have, 38 you said?
Yeah,
38 point, and could have been just slight rounding. I'm going to put 38.667, again, very close within a couple decimal places. Now looking at our diagram, our picture that we drew. Do you think this is a little bit of an over or underestimation? Yeah, everything. Do you see anywhere where it sticks out over the curve anywhere? No. Now it's not by much, but it's going to be slightly underestimate. Any questions on this one? All right, when you're ready, go ahead, turn the page. We'll go to the next one. I don't want to move this if anybody needs it. Anybody still referring to this page? Okay. So approximation 10. Again, you guys had practice with numerous examples on calculating it, so let's get it set up, and then I'll provide you with the answer once we get this set up. So again, we need to subdivide from 1 to 7, and this time units of 1. So we're going to have a trapezoid from there to there. Every unit of 1. We're going to find the area of each of them. So integral from 1 to 7, f of x dx is going to be approximated by, again, we're going to try to write the simplified form right off the bat. We're going to try to do the simplified form. So I know the formula, I always start with a 1/2. Then I'm going to multiply by what? 1, because that's the height of each of them. Good. Now I'm going to try to do all those additions of all my endpoints in the middle. So what am I going to start with? F of 1. What am I going to add to that? Be careful. 2f of 2. So if you think about this, the endpoints, they only occur once. But if you look, we use f of 2 for the first one, and we use f of 2 for the second one. Then we use f of 3 for the second one, and f of 3 for this one. It's an endpoint for 2 of them, all the ones in the middle. So we have f of 1 plus 2 f of 2 plus 2 f of 3. Again, because it's a part of 2 trapezoids. Plus 2 f of 4 plus 2 f of 5 plus 2 f of 6. What about f of 7? Just one of them. Do we understand the reasoning behind that? Okay, again, you have, and you've gone over many examples. You guys know how to plug this into the formula again and add those all together. I feel comfortable that you guys know how to do that. So again, after calculating all of that, you get 39.667. Again, this looks like it's a pretty close estimate, but would you think it would be a little bit of over or underestimation? Under. Yep. Underestimate. All good so far? All right, let's go ahead to the next page then. All right, so you're going to need to refer back to all the examples we have done and the values we have found. So before we start filling this in, let's kind of think of what we've gone through already, because we're going to look at left hand, right hand, midpoint, and trapezoidal. We're going to look at those. But up at the top, just as a reference, you have a left endpoint. And you have some kind of function that's going in this direction. If you start drawing your boxes with a left on the left-hand side, like we did on the first few examples, remember that left-hand side, what was on the curve. So I'm just giving some random example of this. So if you have a left endpoint, and this is increasing, is this an over or underestimation? It's an underestimate. Underestimate. Okay? If you have something that's going in this direction, and you have a left endpoint, this is going to be decreasing function over or underestimate. That's going to be an overestimate. Okay, so that's for left endpoints. If we have right endpoints, again, this will just give you something to refer back to later if you need a reminder. So we have some function that's going in this direction. If we have right endpoints that are on the function, it's going to look something like that. Over or underestimation? Overestimation. If you have some function that is decreasing and you have right hand, this one's going to be underestimation. And let's take a look at the trapezoid next. Trapezoid. So if you have some kind of function that maybe comes down and goes back up this direction, you're going to have a trapezoid, something like this. You have a trapezoid going this way and a trapezoid there. Do you think that's an over or underestimation? Again, this is your function here, and you're always estimating the area under the curve. So we're trying to estimate the area under the curve. Would this be an over or underestimation? It's over. We're estimating the area under the curve, but we're including some of that stuff that's above that curve. So this would be an overestimation. And then if you have something that's concave down, it's more similar to what we just did, having a trapezoid like this. Can you see how that one, like we just did, would be an underestimation? Because there's a little piece under the curve that we're not including. So this is an underestimation. Does anybody have any questions about the three of those? We understand why they're over underestimates? Alright, so what we need to do next, we're going to fill in this table. Again, these numerical approximations are all of the approximations we've already calculated. So you're going to have to look back, fill in the table with the approximations, whether it was an over or under. We have already written that on all the problems, so you just need to go back and figure out what we had written and fill in the table. And then in this box over here, before we get started, it says at this point, place a star next to the approximation that you feel is most accurate to the actual area. Again, that's after you fill in the table. You're going to put a star beside one of these that you think is the closest. And then in the next lesson, we're going to learn how to find the exact area of the region of the graph. And then in the space below, we're going to come back to this later in the section and calculate the actual area and compare the two, the one that we think's the closest compared to what the actual is. So we're going to find out next section how to find the actual one. This one is estimating. So go ahead and look back through all of the notes from the past 2 days, fill in this table, and put a star next to the one you think is the most accurate. How many people are finished filling in that table, just so? Again, once you have them all in there, look at whether they were over or under approximations, look at the values, and try to figure out which one you think is the closest to the actual. All right, finishing up here, looking at the table, which value do you guys feel that was the most accurate? I guess since I don't have the numbers written up here, which one of these do you feel is the most accurate? All right, so I hear an advocate for the last one. Okay, anybody else pick a different one? Dan?
I picked the midpoint Raymond sum intervals of 1 time.
Okay, so that's this one. What were those two values?
The last one was 39.667.
Mine was 40.18.
Okay. So again, comparing those to all the other values you have in your table. Again, I think the actual value for this one that we had gotten within the notes was like 40.167. But looking at those and narrowing them down, keep looking at the over-under. I would definitely agree that it's one of these two is probably the closest. I would probably lean more towards the midpoint one, because if you look at what we were drawing on the midpoint one, you had a little bit over, a little bit under, a little bit over, a little bit under. On the trapezoidal one, yes, it's very close, and it's really close to the curve, but all of the approximation the entire time was under the curve. We underestimated each time we drew a trapezoid. There was no overestimation there to compensate for any of the underestimation. So yes, they're very close, and 39.18, 39.667, not very far apart at all. So we can guarantee that we know it's in between these, because this was an underestimate, this was an overestimate. But in my personal opinion, I would go with the midpoint because we had that little bit of over and underestimation. So this one is probably going to be your closest value to the actual. So that's the one I'm going to put the star by. Now again, we know for sure though that it's between these two values. Okay. So we're probably not going to be able to finish, but let's look at the first example on the next page. And we can at least get started with that, and then that'll have to be finished on Monday. Anybody have any questions on this page? All right. So on page 347, let's look at example A. So we're going to try to use the same reasoning we did, but this time we don't have a graph. They're giving us a table. But we're going to try to use the same mentality we just did. So given the table of values, approximate each definite integral by finding the indicated Riemann sum. So in this, we want to approximate the integral from 0 to 25 of f of x dx. Again, they gave us f of x here. We don't have the actual function. We have the table representing the function. By using a midpoint sum. Okay, so think about the midpoint one that we used. We had, and they say 3 subintervals. So from 0 to 25, they want us to have 3 intervals or 3 different rectangles with the midpoint. So for a midpoint, we have to have that middle value. The middle value is the one that's on the curve. So if we break this down into 3 intervals, if we break this down like this, do we see how there's a value here that can be considered our mid value that would be on the curve? Okay, if I need 3 intervals though, where would my next interval start and go to? So again, with the table, this can be a little confusing, but go ahead, Ariana.
4 to 12.
So be careful of that. We have 4 as the midpoint. This is the end point. So your next one's going to start where the other one ended. So the next one is technically going to start at 7 and go to 15. So in terms of the table, do we understand why they're overlapping? Because they have the same end point. This one's not necessarily going to start on the 4 because that's in the middle, but they have the same end point. Okay? And then the last one, interval would be at 15 to 25. So we have 3 separate intervals. And again, what we're worried about is the midpoint of each one, because we're using the midpoint Riemann sum. Yes, Daniel.
How the heck is 12 the midpoint between 7 and 15?
In terms of the table, the values that are in between, the values they had given us, because they're saying take the table that's given, break this table provided into 3 subintervals. So we have interval here, interval here, interval here, so the 3 intervals. And this is just the midpoint of the intervals provided to us. Okay? Again, if you had the actual graph, they may be a different value than what's there.
Yeah.
So this is the midpoint provided in each one. So again, we're approximating 0 to 25, f of x dx. So what we need to think about in this one, it's not going to be exactly the same as when we actually drew out the midpoint one, because exactly with what Daniel said, they're not all going to be like the same height or length that we referred to. So this first part, we have this interval right here, this first one. What would be considered our height or our length of this first one? 7. We're going from 0 to 7. Remember, we're trying to find the area of each of these rectangles. This represents our first rectangle. It goes from 0 to 7, so we know that distance is 7. Now again, remember, for the height, we want the midpoint. Well, we said the midpoint's in the middle of each of them. Right there is the value of our midpoint. 6. So again, here's the area of our first rectangle. Does that make sense so far, how we found the area of the first one? Again, we need to add the area of all 3 rectangles together. So if we look at the next rectangle, we go from 7 to 15. So what is the height or the length considered of that rectangle? From 7 to 15. 8. It's 8 wide. Okay? And again, look at the midpoint. You calculate, but we don't have to. They give us the table. So the midpoint is negative 10. And the last interval goes from 15 to 25. So the distance from 15 to 25, we know that's a 10. And again, if you look at the midpoint, you get a value of 8. Now I know this is looking at it in a way different way from the graph, but do we understand again why we're overlapping and what those intervals are representing again? Okay, so now to consolidate some terms here, we get 42 minus 80 plus 80. So our final answer, the approximation, is 42. That is the approximation using the midpoint for Riemann sums from 0 to 25 of this function given here. All right, does anybody have any questions at this point? We just have a couple minutes left here. So we're not going to have enough time to start any of the rest of them. So again, this is where it will be picked up on Monday. So Mrs. Bauer will be back Monday, and we'll be picking up with example B. Okay?
Can I go back? Oh, I want to remember.